slide?
Yeah, looks good. Perfect. Bright and clear.
Okay, so I will start with my presentation. As I mentioned already, I will discuss about this new area of photovoltaics. So you can imagine that this is the combination of two worlds, so the photovoltaics and electronics. The basic idea is that we can improve the performance of the PV modules in terms of energy production and also have new functionalities on board of a PV module if we better combine photovoltaic generation, so the solar cells themselves, and the electronics that, as you will see, can be used for different purposes. I will give now some example projects that we have been working on and also some ideas for future work. So the first thing I will discuss is PV reconfiguration. And to discuss about this, we have to first understand what are the problems related to partial shading. So as you've seen, when we talk about modules or panels or even strings and arrays, it's just a combination of solar cells. So let's assume that we have these two solar cells here and that they are subjected to a given irradiation. So we can draw what we call the IV curve. I will be a bit technical on the first two slides, but then it will become easier, let's say. So the IV curve means what is the current that is generated by the solar cells for different operating voltages. As you can see, for the two solar cells under the same irradiation, we have practically the same IV curve. So it means that both of them can generate the same power. And in this specific case is a maximum power of around 4 watts for each cell. But what if one of the cells is shaded? In this case, what happened is that for the same voltage, now we have a lower current level. And if you look at the power for these two solar cells, we can see that the unshaded solar cells could provide 4 watts of energy still, but the shaded solar cell can now provide only 2 watts at most. But this is when we can really control the power production of every solar cell independently. In reality, we need to connect them each other to form the array or the panel or the module or whatever you want. So first thing, we can make what we call a series connection. It means that the same current will flow through the solar cell. Another approach is that we can connect them in parallel, meaning that the current can be split between the solar cells. So for the same voltage, the two solar cells can have different current levels. When it comes to uniform conditions, this is what we happen with the two connections. When we have a series connection, that is the dark black line, we see that the voltage is increasing because they are connected in series, and the current is more or less the same that we had for a single solar cell. When we have a parallel connection instead, we see that the voltage is not increasing now, but it's just the voltage of one cell, but the currents sum up, and we end up with a higher current. If you look at the power curve, we can see that the maximum power is more or less the same, although for the parallel connection, we have a slight less current because of higher losses due to higher current. So what we can say from this part is that if we have a uniform conditions, we would like to have the solar cells connected in series. On the other hand, when we consider partial shading, we see that the IV curve for series connection becomes rather strange, and we have two knees into this IV curve. Because for voltages that are, in this case, below 0.5, one of the two cells cannot really conduct high current, so we need to bypass them somehow, and what I show here is an ideal bypass of the solar cell. Instead, when we have parallel connection, the current can still sum up quite well. Looking at the power, series connection allows us to extract at most, in this case, 4.3 watts, whereas parallel connection allows us to extract up to 6 watts. That is more or less the sum of the two powers that the cells are generated in the maximum power point. So again, if we have uniform condition, we would prefer series connection, but clearly if we have a shading condition, parallel connection could be better. Given this introduction about partial shading, let's see how partial shading is happening in real system and how we can deal with it. In a real system, you already seen this slide. This was shown by Esan, and you can see that even row to row, the modules can be shaded, or there are trees that can shade the module during part of the day, but partial shading is really ubiquitous. You can see here examples of rooftops where there is shade that is blocking this sunlight over many modules of the system. And we need a way to improve performance under partial shading. Our approach is based, first of all, on an analysis through simulation of different shading scenarios. For instance, we can recreate, as Anne showed, a 3D view of this building in Amsterdam. In this specific case, we can calculate the annual irradiation over the module surfaces. Each small square represents the possible position of a cell. And you can see that during the year, there are cells that are mostly in uniform condition and that can have annual irradiation up to 1 megawatt hour per square meter. But there are many places in which you will have much less irradiation. Our idea is to be able to switch between series and parallel configuration of modules according to the shading conditions. So instead of having all the cells in series, we can group the cells as shown here. Then we can have a switching matrix that allows us to reconfigure the module. So when the module is operating in uniform conditions, so all the cells are under the same irradiation, we can still extract maximum power by means of a series connection. On the other hand, if some of these cells are shaded, we can pass to a parallel connection and still be able to extract as much power as possible. We have also done some experiments with this. You can see on the left a mini module that is representative of what was shown in the previous slide. And on the right part, we see a PCB board with many black boxes that are the MOSFETs that allow for the reconfiguration of our system. So from this set of slides, I have one key takeaway for you. So we can design smart PV modules for shade tolerance. It means that we can allow installation in non-ideal locations. If there is a close by building that could shade the module during the day, we can have solution like the configuration that allow us to still increase the power production, even if there is partial shading. However, of course, the higher is the degree of non-uniformity, the more complex could be the module. A limit case is a module where we can control every single cell. So what I mean here is that you can, let's say, not take so much care of shading object, but you should not put shading object on your buildings if you want to integrate on a facade any PV module. Because we have a general solution that can take care of non-uniformities, but it should be not to a very high degree. A second project that I would like to discuss is about custom PV modules. And this can be strictly related to your project. So let's say what engineers and architects would say about this house. An engineer would say, well, it's not that bad. It's a good technical solution. They are using the surfaces quite well. Also, they try to avoid major partial shading issues. That's not bad. Then an architect will say, okay, it could be technically good. I agree with this, but it's quite ugly. And somehow it's also quite boring because it's a repetition of the same shape over and over again. What we can do to, let's say, be more attractive and aesthetically and having aesthetically good solution is to have custom made modules. So we can make, for instance, some mini modules that allow to create different shapes and that can be used on different parts of a building. How can we do this? Well, let's start from a single crystalline silicon cell. We can cut it and then cut it again and cut it again, and we can make it in small pieces. The shape of the pieces can be different, as you can see on this picture, and we can also make the same shape of different sizes. So it means that we can create many different shapes of many different sizes. And of course, this is interesting and good, but as I mentioned before, when there is shading, so when there is non-uniformity, I said, we have different current generation. And in this case, different pieces would have a different active area, and they would also lead to a different type of non-uniformity that is not related to the shade, but to the amount of silicon area that you have in the different pieces. So an optimization is needed here. We should put in series pieces that are more or less the same area so that they can conduct the same current. And when pieces are too small, we can connect them in parallel. For instance, these pieces in the yellow box are more or less of the same area, although yeah, there are some smaller pieces there. But when the pieces are too small, we go for a parallel connection. So we can still increase the voltage to make it usable because we have series connection of many pieces, and keep balancing between the current in the different parts of your system. That means that we can have higher production under uniform condition. What can we make? What you see here is a sailfish, and we can try to remake this same shape of a sailfish, but with PV cells for instance. So we can make something like this. This is kind of a puzzle where only when all the pieces are in place, the system is able to turn on the LED lights that are here on the right of your system. And what is interesting about this solution is that the different pieces have been designed so that the amount of energy that is produced is enough to turn on the LEDs, and they are interconnected both mechanically and electrically through magnets. So the magnets allow us to place the different pieces, but also to have conduction within the different pieces. And we believe this can be a good solution also for any of your ideas. Key takeaway also for this second part. So custom PV modules can be done with cells of different size and shape. And this way we can improve the aesthetics. So you can make nicer PV installations on your facade. However, we have seen also that the difference in size means that the complexity of the design and also the fabrication can be quite high. So feel free to consider different sizes and shape of cells, but take care that the overall area of the different pieces can be, is more or less the same, and they can be easily combined to form a mini module. A third project that we have been working on is the indoor solar lamp that you can see here on this picture. So this is a cable-free solar lamp. The idea is that with PV cells, we generate energy that is stored into batteries, and then these batteries can be used to turn on some LEDs on this lamp. To design this lamp, we need to take into account many specifications and requirements. First of all, we need specific room requirements. We need some insulation in a day into the house, into the room, to make sure that we can recharge the battery at a certain level. For this, we did an analysis of a room. So different orientation of the room. It can be oriented to south, let's say from north to north, as you can see on the x-axis here. And we also consider different distances of this lamp from the window. So what we can see is that if we want to work with an insulation that is at least under 60 watt per square meter per day, watt hour, sorry, per square meter per day, we should work in this area. So it means that the orientation of the room, so where the window is, should be at south, at least plus minus 45 degrees. We should not place the lamp less than 2 meters from, more than 2 meters from the window. We also did an analysis of different technologies, and we think that monocrystalline technology is the best technology for this kind of application. On the other hand, we have the requirements of the product. First of all, it has to be a mobile device. So the only source of energy will be the solar cell. Then we decided to use LEDs for the illumination with 2.5 watt power and 300 lumen. It must be usable at least for 1 hour a day, although we cannot guarantee this same usage in winter. All of these together, we can also, sorry, add that we want the lights to be activated by sensors, either motion sensors or light sensors. So we can pass to the design of the PV module for this application. So what we did, we took high efficiency solar cells and we cut them in 3 pieces, as you can see here. It's important to notice here that cutting solar cells is not the easiest, as you can see, but still we can make it with a laser. We have improved on this and we can have quite good cutting also of these interdigitated by contact solar cells. Then we organized them in 3 different submodules, each of them made of 12 pieces and protected by a bypass diode. The total power of this solar generator in standard test condition, meaning at 1000 watt per square meter and 25 degrees operating temperature, is equal to 36 watt peak. Also, it has to be mobile, so it cannot be so heavy. We replaced the front glass with a transparent foil. So this is much lighter than a standard module of the same size. Also, for the aesthetic, we can use on the back either white back sheet that you can see here also on the corner, this white block, or black back sheet. And this is when it comes to the module design. Then we need the electrical components on top of it. We say that we have the energy generated by the module that is stored in batteries. So we need a charge controller connected to a set of batteries. Then we need a relay that is connected to the sensor and that can activate or deactivate the LED. A driver for the LED to turn them on and off properly, and obviously the LED strip for the illumination. About the sensor system, we have a small video where you can see how it works. So on top, you can see a light sensor that for this video has been blocked, so it will be not activated by the amount of light. And we have the motion sensor active. So when we move in front of the motion sensor, we have the LED on the side that are turned on. The sensor can be also deactivated, and if you click on it, the sensor is not active anymore, and you can also turn on and off the LED manually. What is interesting in that is that the timer of the 30 seconds is still working. So if we now reactivate the motion sensor, it will stay on until we get a false from the motion sensors. Now we move again our hands in front of the motion sensor and we turn on the light once again. This is just one example of how we can integrate different electronics on board of a product, in this case, to make a standard module a solar lamp. In this specific case, the key takeaway is that we can integrate sensor and also actuators that in this case are the LEDs onto the PV modules and enable multifunctionality. In this case, we have a module that is also a lamp. Of course, you can imagine that in this case, it would be much better to use off-the-shelf components for the design, because otherwise it will be quite complex design of all the electronics and in this case, the LEDs around the solar lamp. There are also other concepts and ideas that belong to the photovoltaics area. One of these is to enable data transfer using PV technology. What you see in this figure is a monodirectional communication. On the left, you have a system that through a LED lamp can send a signal that is information in this case, so those are data. And on the right, you can have a solar module, even if they say solar cell, a solar module that can read this information. And with additional electronic, it can do a demodulation of the signal, and you can see this information, for instance, on your computer. Let's say that we are streaming a video, you can see the video on the screen of your computer, and the receiver is the solar module itself. We want to expand on this, and we want to do the communication bidirectional, and we also want to integrate the additional electronics into the PV modules. It's not anymore on top of the PV modules. It can be, as I'm shown before, you have an internal layer of the cells and then you have encapsulation of the module. The additional electronics can be put also within the encapsulation. So it is protected together with the solar cells from the environment. In this case, for instance, we can make LEDs here, and we can use them to send data. So we see that the solar module now is a bidirectional. So it's a transceiver. It can transmit a signal, but it can also receive a signal. If we integrate solar cell, sorry, LEDs, as in this case, you see that they are placed in the empty spaces between the cells. We can also imagine that this can become a media facade, and we can make, with this module, we can send visual signal as well as information in general. Here, the key takeaway is that we can add sensor and actuators, and we will integrate them into the PV modules. So we will enable multifunctionality, as we said before, but we will go beyond the energy generation. It's not only that we use the energy produced by the solar cells, for instance, to power up a solar lamp, but we will also use, for instance, this component to make a transfer of information. And with the integration into the module, we believe that we can also quite improve the aesthetics of the solar, of these new devices. Of course, even in this case, you can imagine solutions that integrate these sensors and actuators into the PV module, but there might be limitation to the number and location of these sensors and actuators. For instance, we will not put these on the surface of the solar cell, but they will be put in the spaces in between the solar cells. A last thing that I would like to discuss is the embedding of storage into the PV modules. You have seen that for the solar lamps, we needed a charge controller and we needed batteries there, but they were just put on the back of the solar lamp itself. I mean, we needed a different case that made also the lamp a bit uglier than it should have been. Another approach is to integrate into the solar module also the batteries with the charge controller, and in this specific case we show a microinverter, so a power electronic system that can connect your PV module to the rest of your electrical system. We have done also in the department some experiments with this, so we can enclose all the batteries and the charge controller in this specific case on the back of a PV panel, and we can make a battery. As I mentioned, that we have to also take into account the balance between production and demand. So it can happen that you are producing a lot at noon, but you need much more power during night. Storage will help to store indeed the energy on location. It will reduce the transmission losses because you can store energy on the place, and you can even reuse it for the appliances in different times of the day where there is no irradiation, or to power up the electronics that is on board of the panel. For instance, if you have LEDs for a transfer of information, you can power up these LEDs through these batteries. A last key takeaway, we will work on plug and play solution that have integrated battery for local storage and that allows to use the energy locally. Of course, you cannot expect that you can add so much storage capacity there because of the battery technology, first of all, and the limited amount of area that we have available on the back of the module. But still, integration of storage is something you can use while thinking about your ideas. So let me wrap up a bit on this photovoltaics discussion, and I will use the same image as I was showing at the beginning. So now try to put onto this image smart and multifunctional models. We have seen that we can face shading issues with shade tolerant, for instance, reconfigurable module. We can make the module nicer using different shapes and forms for the solar cell. We can also integrate storage as well as sensors and electronics, and many more ideas are already in our minds, and I believe they will pop up in your mind too. So imagine this is a media facade, and why don't we make a PV media facade. So we can replace the glass with solar modules that have embedded LEDs. So we can have generation of energy and media facade on the same building. Or think about this office space here. You can see there is some shading here, and we can think about shade tolerant solution to even place modules here. Also, we can think about integrated storage to charge this car that is parked here on this office building. For the lighting, we can use indoor solar lamps, as we showed before. And also, all of the modules could be used for communication. As we've shown before, Wi-Fi communication can be integrated into the modules themselves. And then it's just up to your creativity and imagination what you can do here. I will conclude with the same slide as shown before. So there are many possible solutions and ideas that we worked on and we will work on in the future. And now it's up to you to come up with your own idea. Thank you very much for your attention.
Thank you, Patrizio. Maybe everyone can switch on their microphones. Also to Hesan, thank you very much for this quite elaborative summary of technology and your research. You have changed quite a lot in my knowledge set, honestly. Back then, when I was giving lectures about PV integration, which is already 15, 18 years ago, I was told always make sure that you never put a single PV panel into the shade. That will ruin the entire efficiency and will cause, will question the entire activity of using PV in general. And I was also told that you only are allowed to put the same size of cells next to each other. So therefore, you've also found a solution for that already. Quite interesting.
Yeah, this is still the best practice. If you can avoid shade and have all the cells equal, of course, you will have a better solution.
Yeah.
Now manage all of these issues, much more than.
I'd like to ask the students if they have any questions to ask. Maybe it's wise that we were all muted and we only talk, unmute if you would like to raise a question. Otherwise, yeah, we are now with 70 students in one room, let's say, almost likely. So hit the space bar for temporarily unmute yourself and raise a question if you have. There's also a little wavy hand signal, or you can actually wave your hand in case you have a question.
I actually wanted to know about organic PVs and thin film PVs. And what I wanted to understand was how efficient they are, because I read about dye-based PVs and how it can be painted on a surface. But in terms of output and cost of production.
So, of course, crystalline silicon is still the most efficient technology that you can use. So those technologies like the use of organic materials or thin film are less efficient. I think Esan also mentioned it at the beginning. Thin film is getting better and better. So they are getting efficiency closer to the one that we get with crystalline silicon, but organic is still behind. So there is still some work to be done on the technology. On the cost, thin film technology can be even cheaper than crystalline silicon technology, but it depends, of course, on many factors. And the biggest point is that with thin film technologies, we try to make a single layer. I think you remember from the presentation of S and this long module that was waving. This one usually implies monolithic integration. It means that you have in one process the full module done. You don't have any more single cells here and there. So also the production can be rather limited. You cannot think about cutting easily this type of module. If you want to do something like the sailfish I was showing you with thin film CIGS, for instance, it will be much more complex. So if you want to do that, probably the cost of your solution will be higher in this in that case. So it's really a balance on what you want in terms of aesthetic and what you want in terms of energy production. I hope I answered your question. Eson, if you want to add anything, of course, feel free.
Um, Also, as a follow-up question, for example, if we have a large surface and we have photovoltaics on the whole surface, as opposed to smaller surfaces on the same area,
Okay.
what would be the difference technically and a difference in efficiency and output?
I do not totally get the question.
For example, if we have 100 square meters of area, which
Yes.
is all interconnected and made as one panel,
Okay.
as opposed to dividing it into 10, 10, 10 square meters of area and yeah, disintegration. Does that really affect your output?
If you have uniform conditions and you have the two cases are equivalent because you will have always the cells that can all of them generate the same current level. So as I was showing when I was discussing about the partial shading, you will have all of them connected in series and they will work well. But in
Okay.
the case of there is partial shading, having subsections, and for instance, having the possibility to reconfigure them from series to parallel connection can improve the energy production on the load.
Okay. Thank you.
Any more questions right now? I have one. Patrizio, you mentioned that if we have a tracking device, or maybe it was Hisan, that we are able to gain 18%. Is that true? By tracking the PV panels for a optimized perpendicular orientation towards the sun?
I think it was Esan.
Yes,
Yeah.
it was me.
Yeah.
And the case was for a comparison between a floating PV and also a normal PV installation.
Yeah.
So for that case, we can consider this 18%. But if you, because the system that we have installed, it had limitations with the tracking angle because of the wind load, because we couldn't have the island tumble too much. But if the sky is clear, you can consider up to 35% more power when you do the full dual axis tracking. But the case is for the Netherlands, because most of the time it's cloudy, it's like following the sun doesn't, let's say, make sense that much.
Yeah.
So, but it could be seasonal, huh? In summertime, in the spring, you can do that, but in winter, place it as, let's say, horizontal as possible so it can see the whole sky.
Okay. So you really have to judge it case by case in order to make it, to gain the higher efficiency if you track the PV panels.
Yes, true.
Yeah, okay.
And this is also one of the reasons why we have been working on a simulation framework for this.
Yeah.
Because otherwise you should make an installation for every case. This is not cost effective, but also it takes so much time that you would prefer much more to run a simulation.
Can imagine. Anyone else having a question right now?
I have a question.
No.
Oh, okay.
Go.
Me? Oh, all right. Okay. So I think just now Hassan mentioned about there's a type of silicon sort of PV panels that is like a interdigitated back contacted cells. The one. Just wondering because it has a sort of flexible joint between the panels itself. Just thinking whether these individual panels, are they standardized size or can they be customized to different shapes and then connected into something that can be folded into smaller sizes?
Yeah, both options are possible. So there are commercial modules in the market using IBC cells. And also the in-house mini modules that I have shown in the slides, they are made in our lab. So you can even cut those IBC cells in the presentation that Patricio showed this indoor PV lamp. we manage also to cut the IBC cells. So
Oh.
you can consider them as a, let's say, any random shape, more or less, that you want. You can make it and you can put it on the facade or any idea that you have. So both options are possible.
Right. Then maybe a follow-up question on this is, for the monolithic module, for example, could it have integrated like fault lines in which you can actually, you know, fold it, or is it just a rigid piece that is entirely?
So as far as I know, it can be flexible, but this bending is really depends on how much you want to bend it. So you can, it depends on your case. You can make it, let's say, long strips of cells, but have the joints in a way that you can bend it a little, let's say, more. But it should be in-house. As far as I know, there is not such a thing available commercially.
Yeah.
Sure. Okay.
Is there, Patricio?
I've never seen it indeed. Perhaps we can show the Miura folding. I can share the screen.
Yes, yes.
To give you an idea of what can be done. Okay, I will put in presentation mode. So you see here we have many cells that are interconnected each other somehow, and we can also fold them. This is an origami thing, but still we can make it foldable by cutting the cells in smaller pieces, connecting them as we want them to be connected. This is related to the power we want, of course, from the module, but we can make it smaller for, I don't know, moving it somewhere else or any other application you can think about.
Okay, maybe just one last question, whether PV modules could actually be printed onto other mediums, for example, like canvases or like other more softer I don't know, material. Is it like
This is a great question. It's more for technologists, indeed. There has been research on solar painting, for sure, but I do not know the exact details about it. I can follow up later on the question. I need to check it myself.
It's I guess also depends on the let's say the temperature that this substrate that can handle, huh? Because eventually, if you want to do this lamination for whatever size your target is, that substrate must handle the temperature inside this laminator.
Okay. Yeah. All right. Yeah. Thank you so much.
Okay. Any more questions?
Yeah.
Around?
I was just wondering that I've seen that you can integrate PVs like inside tiles, and I was wondering if that was possible with other materials, like let's say a brick, because the process of producing one is a bit different. And I was wondering if you've ever done testing of like how to integrate it inside a material.
So in our group so far, we haven't done such a thing, at least the one that I know of. But it basically says that if in this project you're going to have your idea developed, and if it's already available, let's say in the market, that they have this PV integrated onto building blocks of the rooftops, then it's also should be possible. But in terms of material analysis, it's not my field of this expertise to say whether it's quickly possible or not.
Mm-hmm. Thank you.
There was also a question in the chat from Georgina. We have been cutting the cells. You remember the slides I've shown you before about cutting the cells. And I think the smallest area we did is 1 centimeter squared cell.
Yes, maybe one thing I can also add. Of course, you can make cells with different sizes, as Patricio mentioned. But if you want to cut a cell and at the same time more or less have a good range of efficiency for the cut version of the cell, based on the research that we did, our colleagues suggest do not go less than 3 by 3 centimeters. But of course, the smaller sizes are also possible.
Any more questions around?
I have a question related to the industry production, and because you show us a lot of experiment that you did in-house, but how flexibly are the industry of the PV panel production? Because if we have an idea, maybe you say, yeah, we can try it in the laboratory, but all the industry is based on panel in the same size with the same technology, and you never will be able to use in outside of academic fields. Or the industry maybe is changing now, and this is my question.
That is another good question. Industry is slightly changing, but changes in the photovoltaic fields are always extremely slow. There are some companies who now work much more than before on custom modules. There are still some limitations, of course. You cannot do whatever you want. You can try whatever you want only in a lab, but when you talk about industry, you cannot do whatever you want. But we see a trend towards BIPV modules. So meaning modules that can reach different aesthetics, that can have different sizes, different shapes, and that can be custom made. It's a slow tendency, but it is there.
Thanks. And I have a second question relate to the same, and is about production, but this industry that are changing now to be more customer product are the high tech or the high quality industry, or the medium or low? Because, for example, I come from a country that the PV cells is very expensive if you compare with the traditional energy. And bring a panel from China is possible, but send a panel from Europe is not possible. And where is located, what is the kind of industry that are changing to more customized?
Oh, there are some in the Netherlands. In Europe, you can find some of these companies. Also, we can also, perhaps I will take a note, we can send a list of companies working on custom-made modules.
I will really appreciate. Thank you very much.
Yeah, maybe a couple of quick names. For example, company Bucky Lab, they're based in Rotterdam, and they're producing, let's say, customized PV modules upon, let's say, an order. But of course, they're produce these modules with a low quantity, and also it's more expensive than the conventional modules, because there is no, let's say, economy of scale for this case. And that's also one of the reasons that the industry, as Patricio said, is moving really slowly towards building integrated PV elements. Also, there is another company, Solarge. They are also working on custom-made PV modules. So if you send an order, then maybe they can process it and make the module for you.
And they are both in the Netherlands, is it?
Yes.
But it's mostly as European, and some of them are also in the US. We'll check just to see if I can find other companies, and I will eventually send them to Marcel.
Perfect, thank you very much. It's also my, in any case, we have later also questions. We will make sure that we will bundle them and then send them to Patricio and Hesan in order to keep them a little bit off, and that they don't have to answer 100 questions per day. Otherwise, I will get kicked ass from their bosses.
Yes.
So we have one last question from Facilica, and then we have to close this session.
Are you hearing me?
Yes.
Okay, so my question is about the PV transparency. How did you get to be the PV panel to be transparent? How much transparency can you reach? And is this PV transparent module can be flexible?
Yeah, so the project that we mentioned, let's say about the transparency was, let's say, a different mode of transparency for the front glass. So we try to make the front glass in a way that it reflects back some portion of spectrum and absorb the rest. But in terms of transparent PV modules, of course, it's possible, and they can also be flexible. I know Patricio can talk more about it, but having them immediately available, it's not the case for now.
Not yet, not yet. There is some research that we are doing also on transparency of PV cells, and we can use thin film materials or different materials, let's say, to get it both flexible and transparent, but it's still research. I mean, we are now working on it. So it's not something we can handle in the short term. Sorry.
Thank you very much. Yeah, what a disappointing answer, ne, Vasilka?